Welcome to The Explainer. Today, we are diving headfirst into a really fascinating research paper that's tackling one of the biggest headaches in AI right now, the insane cost of making models bigger and bigger. We're going to break down a new architecture called Mixture-of-Recursions. It's a super clever idea that promises to give us all the power of a massive AI model, but without the massive cost. So here's our game plan. First, we'll talk about why AI scaling is such a problem. Then, we'll introduce the star of the show, Mixture-of-Recursions, or MoR. We'll get into the nitty-gritty of how it works, then look at the hard data, the proof, to see how it stacks up against other models. And finally, we'll zoom out and talk about what this could mean for the future of AI. For the longest time, the motto in AI has basically been bigger is better. But when you scale these models up to hundreds of billions or even trillions of parameters, well, the computational power and memory you need just explodes. It's become this kind of unsustainable arms race, and it's getting really tough to compete unless you're one of the tech giants. And that gets you thinking, is just making models bigger and bigger the only way to make them smarter? Or could there be a more clever, more efficient way to get to that same powerful AI? Well, historically, researchers have really come at this from two different directions. The first path is something called parameter sharing. The idea is to keep your model small but deep by just reusing the same layers over and over again. The second path is adaptive computation. This is all about intelligently deciding where to spend your energy, focusing your compute power only on the really hard parts of a problem. But here's the thing. These two incredibly powerful ideas have pretty much existed in separate worlds until now. And this is where things get really interesting. Researchers came up with a new framework that finally gets the best of both worlds. It's called Mixture-of-Recursions, or MoR for short. The core idea behind MoR is so simple, but it's also incredibly powerful. Just imagine a model that not only reuses its core knowledge to be super efficient, but can also decide, on the fly, how much thinking to apply to every single piece of data it sees. It could spend a lot of time pondering a complex word, but just breeze right past the simple ones. So how does this actually work? Well, technically, MoR is built on what's called a recursive transformer. So instead of having hundreds of different, unique layers, it just has one single block of layers that it can use again and again. That's the parameter sharing part. But here's the cool part. MoR adds these little things called routers that decide for each token how many times it needs to go through that block. That's the adaptive computation happening at a really, really granular level. The authors of the paper sum it up perfectly. They say, MoR ties weights to cut parameters, routes tokens to cut redundant flops, and caches key values to cut memory traffic, all in one architecture. Let's quickly break that down. Tying weights, that's the parameter sharing. Routing tokens, that's the adaptive part. And flops are just the basic unit of computing power. So MoR makes the model smaller and reduces the amount of raw calculation it does. And it even makes memory use more efficient. It's like a three-pronged attack on inefficiency. Okay, so let's get into the nuts and bolts. How does a model actually make these smart routing decisions and manage its memory so well? It really comes down to two key design choices. First, let's talk about routing. One way to do it is with expert choice. Here, each processing step acts like an expert and just grabs the most important tokens to work on. Now, this is great for keeping your GPUs busy and balanced. But there's a catch. It breaks a fundamental rule of language models called causality. A model should only know about the words that came before the one it's predicting. Expert choice has to peek at the whole sentence to find the important tokens, which is a no-no. The other way is token choice. Here, each token decides for itself at the very beginning how much work it needs. This totally respects causality, but you can end up with some hardware getting overloaded while other parts are just sitting around. Second, there's memory management. When a model reads text, it keeps a kind of short-term memory called the KV cache. MoR has two clever ways of handling this. With recursion-wise caching, a token's memory is only active for the specific steps it's being processed in. This saves a ton of memory traffic. The other option, recursive sharing, is even more stingy with memory. The cache is made once, right at the beginning, and then shared across all the steps. The trade-off is, this actually makes the attention part of the calculation a little less efficient. All right, so the theory sounds great, it's elegant, but does it actually work in practice? Let's get to the good stuff, the results, and see how MoR actually performs when you put it up against a standard model. And the numbers really do speak for themselves. Just look at the parameters column. The MoR model is almost half the size of the standard vanilla model. Now look at the performance columns. It gets a lower error score, which is good, and a higher accuracy score. I mean, think about that. You get better performance with a model that is nearly half the size. That is a massive win. And get this, it's not just more accurate, it's way, way faster. This chart shows us the inference speed. The standard vanilla model is our baseline at 1x speed. The MoR model with 2 recursion steps is already 1.6 times faster. And with 4 recursion steps, it hits an incredible speed up of over 2x. That's just wild. So how is that even possible? How do you get more than double the speed? It's because of this really clever design where some tokens can exit early. Think of it like an express lane on the highway. Because some tokens finish their journey early, the GPU doesn't have to wait around for the whole batch to be done. It can just immediately start working on new tokens, which keeps the hardware constantly busy and cranks up the overall speed. This chart, for me, really drives the point home. It's called an ISO flop analysis. ISO means same, and flop is just a unit of computation. So what this means is that all 3 of these models were trained using the exact same amount of compute, the same energy budget. And as you can clearly see, the MoR model achieved the lowest loss. It learned more effectively from the exact same amount of work. It is, simply put, a more efficient learner. So let's wrap this up. What does all of this really mean for the future of AI? Where does this breakthrough take us? Well, this research just blows the doors open for what comes next. For example, you have this idea of latent reasoning. Since MoR can choose to think longer on a tough problem, you could actually train it to do complex multi-step reasoning before it gives you an answer. And because it's so efficient, something like multimodal expansion becomes really exciting, applying this smarter way of thinking not just to text, but to way more complex data like video, audio, or even scientific data. And that brings us to the final big question. This work from the MoR paper really suggests a shift in how we think about building AI. Maybe the future isn't this endless arms race for bigger and bigger brains, but a more thoughtful search for architectures that can think smarter, not just harder. Thanks for joining me on The Explainer.